This video is going to be on finding the extrema of a function. So first we'll go ahead and define what each of the extrema are. So the first is the absolute max, and so this is the highest point in the function. And this happens at a coordinate, an x and a y coordinate. And so the x value is the location of the absolute max. And the y coordinate is the value of the absolute max. So for example, if the absolute max was like at 517, then we would say the absolute max is at 5 and has a value of 17. So there's a difference between what the absolute max is and what its value is. So the absolute max, or the location of it, is the x coordinate. The value of it is the y coordinate. And that notation and that understanding of what it means is true for the absolute max and the min and the relative max and the relative min. All right, so the absolute min is the lowest point in the function. And then we have the relative max, which is also known as the local max. And that, I'm going to write down the formal math definition, and I'm going to write down what it actually means. So I'm going to say at c, so at an x value of c, then f of c is greater than or equal to f of x when x is near c. So this means that for all the x's that are by a certain number, the y value when you plug in that number is bigger than all those than all those y values when you plug in all those x's around them would be. So basically this is talking about a highest point in an area. So it may not be absolutely the highest. That's what the absolute max is, like the very highest point you can possibly find. The relative max is just the highest maximum in that area. So it looks kind of like a mountaintop. That might be something you could write off to the side in your notes. So we also have a relative min, or a local min. And the definition is similar. So at c, f of c is less than or equal to f of x when x is near c. So this would be the lowest point in an area. So it's saying, oops, sorry. There we go. So it's saying the y coordinate you get when you plug in c should be less than the y coordinates you get when you plug in all the x's that are near it. And so that means that that y would be lower than the rest of them. And it's not absolutely the lowest, it's just lower than the things that are in its general area. All right, so we're going to go ahead and draw a picture, and we're going to label the extrema in the picture. It is not important that your picture looks exactly the same as mine, just like generally the same is fine. I'm going to say this is point A, point B, point C, D, E. So at x equals a, that is an absolute minimum. That is the very lowest possible point in the graph you can get. At D, we have the absolute maximum. That is the very highest point you can possibly have. Now, if we look here, this is not the absolute highest point, but for the little area that it's in, it's considered a high point. And so we're going to say that this is the relative max. C is not the very lowest point, but in the area that it's in, it's a low point. So this would be the relative min. D, not only is it the absolute highest point on the graph, but it's also a high point for the area that it's in. So while we'll call it an absolute max, we can also call it a relative max. And then E is nothing. It's not a relative min because it's not the lowest in the area that it's in. We have to think of those as being like valleys. So we need to have points on either side of it for it to be considered a min. So it's not a low point, it's not a high point, we're just going to say none. It has no special name. All right, so what is special about relative extrema? So relative extrema is like right here and right here and right there. And what's special about them is they have horizontal tangent lines. They have horizontal tangent lines, which means that their slope is 0. Sorry, I keep doing that. I'm going to do a better job. They have horizontal tangent lines. That means their slope, or the slope of the derivative at that point, would be 0. All right, there's one more word that we want to define, and that word is, or that place on the graph, is called a critical number. So a critical number is a number C in the domain of f. So when I say it's in the domain of f, that just means that C can be plugged into the function and actually get an answer, such that f prime of C equals 0, or f prime of C does not exist. So f prime of C equaling 0 tells us that we're talking about horizontal tangents. When we say that f prime of C does not exist, there's a lot of different reasons that we could say something doesn't exist. That might be because we have a vertical tangent line there. It might be that we have a cusp or a sharp corner. So some picture examples of critical numbers could be like the curve does this, and we have a cusp right there. That would be a critical number. It could be these maximums or minimums. Those are critical numbers because the derivative there is a horizontal tangent, right? So we have a horizontal tangent line. That means we have a slope of 0, so the derivative would equal 0. A corner would also do it, so that would be a critical number right there. And then also if we consider something that looks like this, it's not a maximum or a minimum, but we would have a horizontal tangent line there, so that's a critical number. So some of our critical numbers will be extrema, but not all of them. It's just a good place to start looking for your extrema. So we're going to say some critical numbers are not extrema, but it's a good place to look for them. All right, so every function, one thing we should know is that every function on a closed interval, and closed interval just means that if you were to describe the x's or describe the domain for the picture, that you would say it's in between one number and another number, and those two numbers would be included in brackets. So we're not talking about negative infinity to positive infinity. That's parentheses, that's an open interval. A closed interval says, look at the graph, but only look from 1 to 5. And you're including 1 and you're including 5. So every function on a closed interval has an absolute max, and an absolute min, if it is continuous. So if you look at the graph and it's a continuous graph, then there's definitely going to be a highest point and a lowest point somewhere on that graph, as long as we've cut it off and we've said it's between two different numbers. If you talk about negative infinity and positive infinity, then you start to get that idea that the highest point could be an infinity, and that's not really a number, and so we would say there isn't really an answer there, and that's where things start to get confusing. All right, so the next thing we want to look at is how do we find these maximums and minimums, like how do we do this by hand? So we're going to learn the extreme value theorem. Which we will call EVT for short, so we don't have to write it out every time. And the extreme value theorem says that if f is continuous, on a closed interval, then f has an absolute max value, and since we're talking absolute max value, we're talking about a y-coordinate here. So it has an absolute max value, f of c, and an absolute min value, f of d, at some c and d. So we're saying that it has a highest value, that's a y-coordinate when you plug in c. It has a lowest value, that's the y-coordinate when you plug in d. And so these are at some x value that are c and d. So we're plugging these in for x, c and d. And we're going to say that they are on AB, and that means that it's somewhere between those numbers. It could equal A, it could equal B, or it could be in between them. So somewhere in between those numbers, we're going to have a highest value and a lowest value. So I'm going to go ahead and draw some pictures of this so you guys can see how this would look. So it could be that this is A and this is B, and that would mean that our highest point is right here. So this is the value we're plugging in for C, and f of C is up here, and this is the value we're plugging in for D, and f of D is down here, because that's our maximum, that's our minimum. It could be that we're looking at something like this, where we have two minimums. If you can see that our absolute minimum, there would be two of them. They're kind of at the same point. So I could say that our minimum, our D value, could be here or it could be there. Those would be about the same. And then our maximum value would be somewhere in between. So somewhere in between, I plugged in a C value and got a maximum up there. It could be saying that my absolute maximum is right up here, so I plugged in C and got this point, and I plugged in D and got this absolute minimum down here. So that would work for what I'm saying. Now this one is interesting because absolute maximum and absolute minimum are actually the same point, because all of these y-coordinates are the same. So we could say that A and B are on the ends, and then C and D could really be anywhere on that line and it would still work. But we have one circumstance that does not work. And that is something that would look like a piecewise function like this, where the function itself is not continuous. And so here we would say that the extreme value theorem does not apply. So, and all these pictures were good because we had continuous pieces of the graph, but over here this is not continuous, so it would not work there. So, to find absolute extrema, we have 4 steps to follow. So here's a closed interval. So to find absolute extrema on a closed interval, first you need to verify that the extreme value theorem would work. And so that means you need to check and see if your graph is continuous on that interval. Second, you need to find all critical points. On the interval AB. So we don't care what's happening at A and what's happening at B. That's why I said it's an open interval now, because we're not including A and we're not including B. I just want to see what's happening in between those numbers. So find those critical points, and remember, critical points happen when the derivative gives us a slope of 0 or an undefined slope. So those are the 2 things that we look for, where our derivative equals 0 or our derivative is undefined. Third, we want to evaluate the function. At the critical points and the endpoints, and the endpoints are A and B. I should not write it like that, that's confusing. So that means that that's partially why in number 2, when we find our critical points, we don't care what's happening at A and B because we already have to use those anyway. So we evaluate the function. And then fourth, we identify the absolute max and min. And at that point, it's pretty straightforward. It's very easy to identify which is which. Okay, so we're going to move on to examples. So the instructions might say something like find the absolute extrema on the closed interval. So the first problem we're going to look at is the function f of x equals x to the 3/5 times 4 minus x, and this is on the interval -1, 2. So the first thing you want to do is you want to check to see if it's continuous, and graphs that are not continuous might be rational functions where there's some sort of number that would make the denominator equal 0, or radical functions, because if you take an even number root, a square root, a 4th root, a 6th root, you can't do that to a negative number. We almost should be concerned here because this is a 5th root, but since it's an odd root, we don't have to worry about it. Piecewise functions would also be where we're going to look for graphs that are not continuous. So there is no reason for us to expect this to not be continuous. So first I'm going to say that this is continuous on -1, 2. And so that means that the extreme value theorem applies to the problem, so that's good. So after this, we have to go ahead and find all the critical points. And we do that by taking the derivative of f of x. So to make my life a little bit here, when I find that derivative, I don't really feel like doing the product rule if I don't have to. So I'm going to go ahead and just distribute this. That gives me 4x to the 3/5 minus x to the 1 and x to the 3/5. If I were to multiply those together, I would add the exponents. So 3/5 and 5/5 gives me 8/5. And again, I'm just doing that because I don't feel like doing the product rule when I find this derivative. So now I'm going to go ahead and find the derivative of this problem. So I've got, for the first one, I'm going to drop the exponent down to the front. So 4 times 3/5 would give me 12/5. X to the negative 2/5 minus, if I drop that down to the front, I've got 8/5 x to the 3/5. And now I need to go ahead and kind of simplify that derivative that I have. So this gives me 12 over 5 x to the 2/5 minus 8 x to the 3/5, and that's all over 5. And the part about this that makes this problem kind of a bummer is if we look back at our notes to remember what critical numbers are. Critical numbers are where the derivative equals 0 and where the derivative does not exist. And that is if you have, the easiest way to think about doing this is if your derivative is a fraction, the derivative equals 0 when the top of the fraction equals 0, and it does not exist when the bottom of the fraction does not equal 0. So if I look over here, I can't evaluate it the way it looks right now because I don't have this written as one fraction. That means I have to get a common denominator. So I am going to multiply. I can see that both of these have a 5. So now if they both had an x to the 2/5, so x to the 2/5 on the bottom and the top, I'm getting myself a common denominator. If I can do that, then I can get to the place where I'm going to be evaluating this derivative to see where each of those things is happening. So I have my common denominator of 5x to the 2/5. And for the numerator, this one stayed 12, nothing happened to it. And then over here, the 8 stays, and if I look at my exponents, I have x to the 3/5 and x to the 2/5. And to do that, I would add my exponents together. So 3/5 plus 2/5 is 5/5, and that's just x to the 1 power. All right, so where I do the part where I'm looking for where my derivative equals 0, that's going to be me taking the top and setting that equal to 0. For the other part of finding the critical number, where I look where my derivative is undefined or does not exist, then I'm going to say that that's the bottom, equaling 0. So I'm going to go ahead and add 8x to the other side. So that gives me 12 equals 8x. And then I will divide each side by 8 to get the x alone. So I have x equals 12/8. And that's the same as saying divide by 4 on the top and I get 3, divide by 4 on the bottom and I get 2. Over here, I'll divide each side by 5, and that gives me x to the 2/5 equals 0, because 0 divided by 5 is still 0. And then if I was to get rid of this exponent, I could raise it to the 5/2. That would get rid of it. But either way, I think it's pretty clear that 0 to any exponent is what would give you 0 here. So that x value is 0. So we've done the first step. We verified that the extreme value theorem is going to work. Second, we found our critical points. Now we need to evaluate the function at those critical points. So I want to take the original function and plug in 3/2. I want to plug in 0, so those were the critical values. And then I want to plug in those endpoints, which is -1 and 2. So those are x values for those endpoints. They were basically telling us what the domain of our function was. So 3/2, 0, -1, and 2. And for me to evaluate this, I'm actually going to ask you guys to typically just graph this. And the reason is that can help you it can help you evaluate it easily, but it can also help you check your answers as you go, which is kind of nice. So I went ahead and graphed it. And now to evaluate it at those numbers, I'm going to let it graph. And then if you hit second trace and use option number 1, that allows you to plug in any x value that you want. So I'm going to plug in 3 divided by 2 first, and that's this point up here. And you might already look at that and be like, well, that's probably the maximum, and it probably is. So that equals 3.189. If I plug in 0, I get 0 for y. And if you guys can see, that looks like, it almost looks like a vertical tangent line. Yeah, and that's where our vertical tangent line was, so that makes sense. If I plug in -1, I get -5. And then if I plug in 2, I get 3.031. So if we look at these numbers, this number was the very highest we could see, so we're going to say that that's where our absolute max is. So the absolute max is located at 3/2, but the absolute max value is 3.189. And then here is our absolute min, so it's located at -1, but the absolute min value is -5. And we will do more examples in class because this video is long enough.